So I'm Ojaswa Sharma. I am from CSE department at IIIT Delhi, where I work within computer graphics and computational geometry. I'm also affiliated with the maths department here. So this is our some of our work from our research lab. We call it the graphics research group, where we do a lot of work within computer graphics in general, computational geometry, shape creation, modeling, and a lot of work also on medical imaging. The left hand side, if you see, is we work with a lot with medical data, how to visualize medical data. If you have seen CT or MRI scans, how many have seen CT MRI scans? What color are they? Gray, right? Gray, black, shades of white, black, right? Now, one of the tasks is how would you visualize it in color? Okay, so we do a lot on that, and recently also using AI-based methods to colorize. Then in the center you can see some of our work on geometry creation. We create a lot of procedural geometry. How would you replicate real life shapes, for example, right? And that's one of the interesting problems that you might as well want to explore after you're done with the summer school, because such geometry is very, very useful. It's useful in industry, it's useful in entertainment, CAD CAM geometry you can create. Then you can create geometry for augmented and virtual reality, right? Because in AR, how many have experienced VR before? Raise your hands. What type of VR? What equipment was it? Right. So did you wear a headset? Which one was that? HTC Vive or Oculus Rift, or was it a mobile based? Right. So it must have been HTC Vive or cousins of HTC Vive. So basically this is nothing but a display. So it's a stereo display. Everybody knows what is a stereo? I don't want to get into a stereo and all, but do you know what is stereo? No? You do it every day. Even now you're using stereo vision. We have two eyes. We see with both of our eyes, and there is a slight separation between our eyes, right? So basically in your brain we register two images, a left image and a right image, and our brain fuses these two images and creates a 3D representation of what we are looking at. In fact, we are looking at 3D, but these lenses and because of these lenses, everything gets projected onto the retina, and that's a two-dimensional image, right? Now these two-dimensional images are fused by our brain into a 3D representation, and that's how human beings see in 3D. This is called stereo vision, okay? And the same has been done in computer vision. You can take two cameras, take similar cameras, that's better if they are similar cameras, and then capture two images. Then there are algorithms, computer vision algorithms, with which you can fuse them. And is anybody aware of these algorithms? No? Multi-view stereo algorithms? Anyway, we are not covering those today, but just for your knowledge, okay? And I forgot why I went to multi-view stereo, but because you can use that to recreate geometry. Could use that to recreate real life geometry. And today there are a lot of tools that would allow you to recreate real life geometry. So we did some work on that, and then of course we work on AR VR. So I'm not really going very deep into it because time is less and I have a lot to cover today, but that is just some overview of what we do. And just quickly see okay, this is all just in detail, so I'll skip that, and maybe I'll start with the lecture for today. Okay, so today we are going to look at implicit and discrete surfaces. What you have looked at so far, basics in linear algebra the first day, and then you looked at curves and surfaces the second day, and third day you had a brief introduction to computational geometry. And within computational geometry, I believe you looked at Delaunay triangulation, Voronoi diagram. What else? What else did you You're going back and looking at the notes? Sorry? Splines, you looked at Bezier. Basically, the first day was curves and surfaces was parametric representation, okay? That's one type of representation. I'm going to discuss today two more types of representations. One is called the implicit representation, a very, very powerful representation. So please pay attention to what I'm discussing today in the first half. In the second half, I'm going to discuss what is known as the discrete representation, which is again very powerful and very widely used. Okay, so every representation has its strengths, right? So you might want to use one representation over the other depending on what problem you have at hand. Okay, and I have created very short demos in between where I will tell you, where I'll show you how things work basically. Okay, just to get more understanding of it. So, and maybe some little exercises in between. The afternoon session will be taken by one of my students, Gaurav here, who will take you through some exercises in Python. My demos today are in MATLAB because I'm well versed with MATLAB. I don't do too much Python, but you don't have to do any programming. You could just take a look at the demos. That the construct, the language itself isn't very difficult, so you should be able to follow what has been written there. And I will tell you what it means. Okay, so don't worry that it is MATLAB, you won't understand, won't happen. Okay, so let's begin with this. Right, so this is our this is sort of our outline for today. The implicit within implicit surfaces, we are going to look at three things. Sorry. Oh, it doesn't change. Okay, we need to see why it's not changing. Now it's changing. There's been some delay, I believe. Oh, now it's fine. Now it's fine. Okay. So we will look at implicit surfaces first, how to define them, what are these. You already know the basic outline, I believe, from your, I don't know, maybe school time or we'll see. Then we will see a special type of implicit function known as the signed distance function, or signed distance field is how it is known usually. Very, very useful type of implicit. Why so useful? Because you can potentially represent any shape, any arbitrary shape with a signed distance function, and I'll tell you how to compute it with example in my demos. Okay. Then we will see level set and polygonization. Some of you from maths background might be aware of what is a level set. Anybody from maths background? Have you heard level set before? No? Anyway, don't worry, we'll cover that. Polygonization, and hopefully we'll have a break then, and post break I'm going to take you through discrete surfaces and data structures. Again, very important, because you know, like you have data structures to store, like you have trees and linked lists, you have certain spatial data structures. These spatial data structures are called so because they store spatial data, right? They store geometric data, right? So you might think now that, you know, they're data structures. Why do you need a data structure? I mean, can't you just store everything in an array? And yes, the answer is you can store things in arrays. That's a very simple type of representation, but it may not be optimal for certain things. For example, searching. You want to search for a point or any primitive for a triangle, for example. It's the complexity would be high. So you need special data structures so that those may be optimized for search. Some might be optimized for display. Some might be optimized for editing the shape, for example, right? So we will look at one such important data structure today, and I'll go through some of the operations on it, which would be useful to you tomorrow as well. When you look at I think tomorrow is Laplace-Beltrami, probably, right? So that we will do, and then we'll look at subdivision surfaces, which is used to create high quality surfaces from a low quality surface. Now when I say surface here, I mean a discrete surface, and I know you don't know what is a discrete surface, but we'll learn that. Okay. Then again, I had Delaunay, but that's more like a quick overview, so I'm not going to spend time on Delaunay here. But you didn't cover CDT yesterday, a constrained Delaunay, or did you? Constrained Delaunay, did you cover that yesterday? No? Okay, just a slight extension to Delaunay triangulation. I thought this might just complete the loop, so I had it included here. And you did Voronoi diagram yesterday. I'm going to extend that. It's good that you already know what is Voronoi, so we'll use that definition and learn what is known as the medial axis. Again, a very important concept. All right, and then if time permits, surface reconstruction, but maybe not, because I think this is still already too much. Okay, and please ask questions in between. I would love to hear from you. So right, so first, implicit surfaces. Let us see what is geometry. Geometry comes in various shapes and forms, and therefore it is required that we have different forms of representations for geometry. So usually geometry is like any signal, right? Anybody from EE, electrical electronics background here? Signals, right? Do you remember the Nyquist theorem, Shannon's theorem? What is Shannon's theorem? So okay, I'll let me. So if you have any signal and you want to represent it, you want to capture it or you want to store it, right? You need to sample it. What is sampling? Is that you go to the signal and say, okay, at this point, what is the value, right? And you do that at many different points. For example, audio. When I'm speaking now, it is being stored somewhere, maybe in an MP3 or in an audio channel of a video stream. It has to be sampled. Videos are also sampled, at a certain frame rate. You watch any movie that's 30 FPS, let's say. That means 30 frames per second have been captured. That means 30 photographs in a second, played out in a succession, right? So what is this 30 FPS? It is sampling. Similarly, when you hear out an MP3, it will have a certain rate, sampling rate. Because this is a more advanced sampling rates in MP3s could be, it could be variable bit rate or fixed bit rate or whatever, right? But apart from that, you have to sample a signal in order to capture it. Okay. Now, Shannon's theorem says that you have to sample a signal by at least twice the highest frequency present in the signal. Correct me if I'm not from that background, but I know Shannon's theorem. Is it correct? You have to sample the signal at twice the highest frequency present in the signal for a perfect reconstruction. So what do I mean by that? So let's say you have a one-dimensional signal. Okay, let this be the signal, right? And that's your time, and let's say that's your amplitude. Okay, so you want to capture, you can't store this signal. It's an analog signal. You don't know the equation, so you can't store it. So what do? You have to sample it at a certain points. So x0, x1, x2. Now Shannon says if you do not sample it at a certain rate, at a certain minimum rate, you're going to miss out certain details. That is, so let's say now I have only these sample points and I need to reconstruct the signal. What is the best that you can do? You could connect them by straight lines because you don't know what has happened in between. So you're going to lose out on things that are not sampled, right? So what's the solution? How could you make sure that details like this are sampled? And this is considered as a high frequency detail that you missed out because you didn't sample fast enough or frequent enough. So you missed out on this detail, right? So Shannon says sample the signal with twice the highest frequency present in the signal, right? Now signal, it's a 1D signal, so you could do a Fourier decomposition, find out what's the highest frequency, and then sample at twice that rate, and you'll be fine, you'll be safe. Okay, so you have to sample signals, and that's true for any data. It's true for images. Now could somebody tell me, this is for 1D signals, how are images sampled? In all of you have cameras. How does things get sampled? in a camera? How is sampling happening in an image captured through a camera? Pixels, right? Inside your camera there is a sensor, right? When you say 20 megapixels, what is this 20 megapixels? It's the number of pixels present in an image that comes out of the camera, right? But inside your camera there's a lens assembly, and that focuses all of the light coming through that aperture onto the sensor. Okay, there are different types of sensors, but each sensor in a sense has these light sensitive diodes. Okay, these sensors, they allow they convert light into electrical signals, and for every pixel you have RGB sensors, so they convert light into red, green and blue components. Now there's a different story that I can tell you about why red, green and blue, and how red, green and blue is able to represent all the millions and zillions of colors. The human eye is sensitive to a lot of colors, but can somebody tell me how many maximum number of colors that a RGB image out of your camera can capture? 256 raised to power 3, which is exactly 16 million colors, right? Human eye is capable of distinguishing or seeing many more colors than 16 million, but it's a limitation of our hardware, right? So it's not right. So our displays, displays like this, they can't display more than 16 million colors. Okay, now you have these. So why 888 image? RGB images are also known as RGB 888 because they are 8-bit per channel images. Okay, so 8-bit per channel. That says that's why you have 24-bit images, but you can also have 10-bit per channel. You can have 12 bits per channel, 11 bits, right? Possible, but not good use, because in everyday use you won't be able to see them on the computer screen. The computer will have to then convert it into 8 bits per channel and then display. Right? Now, if you go very close to your computer screens, you will notice that every pixel on your computer screen has red, green and blue light emitting diodes. Okay, so it's basically them doing the reverse. Okay, so whatever values are stored in a pixel of your image, it's going to emit that much light. We will try to approximate that much light so as to be faithful to the image that you capture, but in real life it doesn't happen. If you see two displays, your phone display and your computer display, there will be difference, right? You must have observed that. So anyway, so you have to sample images, you sample in pixels. Then how would you sample for shapes? How can you sample shapes? Sorry? Yes, you have to take help of geometry. So there are multiple ways. Okay, so that's why we have different representations. We have discrete representations or explicit representations. Sorry?
Dot clouds.
Sorry?
Dot clouds.
Point clouds. Point clouds. These are called point clouds, right? Point clouds, yes. So that is an explicit or discrete representation. So you have mesh. You can store them as meshes. That is, you convert the geometry into triangles. So the surface is converted into a triangulation. I'll explain you what is a triangulation. It's basically a tessellation. Tessellation, new word. Tessellation, everybody knows what is tessellation? No? Okay. So tessellation, to tessellate something. Can somebody check the spelling? I think tessellation, I might have gone a little bit wrong here, but a tessellation is a tiling, tessellation or tiling. So if I have, let's say, a hexagon and I continue 1, 2, 3, 4, 5, 6. I continue doing this. Okay, 1, 2, 3, 4, 5, 6. Yeah, I can keep on doing this. This is a hexagonal tiling or hexagonal tessellation. Okay. Then you can have triangular tiling. So you have triangles around. And we are going to be discussing a lot of triangulations today. What more can I have? I can have a quad tiling. I can have quadrilaterals, right? So I can have quads. Okay. So these are tessellations. A mesh is nothing but a tessellation. Okay, you can have 2D tessellation, you can have 3D tessellation, 4D, blah 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 blah. Okay, so that is an explicit representation. Now a tessellation has a topology, and I'll talk about that in a moment. But let's go one step back. Before you do tessellate, you have points, right? It is basically connecting these points with each other in a certain fashion, right? So these were the points. So the point clouds that you talked about, right? The point cloud, you connect them in certain way to tessellate. Okay, but the first representation is points or point clouds. So if I have a laser scanner, I could scan this entire room and get millions of points. That's my point cloud. Okay, I can probably show you some point cloud as well. Let me see. Right, and then you tessellate it. You basically create a mesh out of it. Right, so polygonal mesh, triangle mesh. A triangle mesh is a triangulation. Triangle mesh is triangulation. Triangle mesh. Triangle mesh is. Okay, right. So that's one representation we'll look at today. Then there is implicit representation, which is a voxel based representation, a volumetric representation. You all have seen images, right? Pixels have certain values. In your case, pixels have RGB values, which is a vector value, right? RGB is 3 component, so it's a vector of 3 numbers, right? So it's like a vector field. Everybody understands what is a field? So what is an image? An image I is from R2 to R3. So basically it takes your XY point to RGB color. So that's in a sense a vector field. Okay, if you have a grayscale, let's say you have a thermal image. Thermal images are single channel. So that would be a scalar field. So thermal image, let's say, just an example, okay? Just an example, a thermal image would again be, it's a 2D image, so R2, the domain is 2-dimensional and it goes to R, okay? Actually is subset of R, so XY to some intensity I, let's not assign any color to it, okay? In fact, these RGB are 3 channel, that means they are 3 those correspond to 3 frequencies of light. Like thermal corresponds to 1 frequency of light, RGB is 3 frequencies of light. It's the nature of human vision that you can mix RGB colors in certain proportions and produce any other color. Not produce any other color, but we perceive as any other color, right? This is the property of human vision, not a property of light. That is to say that you can't mix red, green and blue photons to create a purple photon. No, you can't create that. You can't create a purple colored photon, but you could fool a person to see a purple color with a combination of red, green and blue, right? And that's what these photographs and all of this digital colorimetry does. Okay, and then the third one is parametric, which Professor Ramanathan has already explained yesterday very well, right? So parametric you very well know. I'm not going to touch on that topic today, but we'll look at implicit and discrete. So implicit representation. What is an implicit representation? Now, an implicit function, right? An implicit function is defined as a function f that when applied to a point P gives you a value, a certain value, okay? So it gives you a scalar value. So that's an implicit representation, implicit function. For example, the equation of a circle, right? X square, circle centered at the origin, right? So x square plus y square minus r square. This function is an implicit function, right? So we have just moved the r square to the left hand side and gotten rid of that equation. Now this function f, what is this function f? This function f takes from R2 to R. Everybody agrees to that, right? Anybody who doesn't, please raise your hand. I want this point to be clear. this function takes a point to a scalar value. That is an x. You plug in this function, you plug in an xy value, you get out a number, a single number, right? Now this is a circle, right? So what can I say about it? Now for one thing is for there would be some xy values for which this function would be negative, right? Some xy values would result, and in fact all those xy values that are inside that circle would result in an f function value of that is negative, right? At the periphery, that is at the circle, what would be the function value? Exactly 0, right? Because that's how the function has been constructed. And outside that function, outside that circle, the value would be positive. Okay, that would be the case. So how can I represent a curve in the implicit form? Well, I can say in the set form I can represent. So a curve S is a set of all xy points for which fxy takes a value of 0. Please note that. Okay. So how do I the curve is circle in this case. The curve S is a set. It's a set. Okay. It's a set of all xy points, a collection of all xy points for which this function takes a value of 0. Right? I have a demo, so don't go to sleep yet. This is, so fxy equals to 0. Is there anything special about fxy equals to 0, or can I take any value here instead of 0? Can I say 1? If let's say r is greater than 1, can I say fxy equals to 1? It could be there, but what circle would that be? A bigger circle. Let's see if it's going to be a bigger circle or a smaller circle. But there is nothing sacrosanct about 0. I could put in any scalar k there, right? This is called the 0th level set of this implicit function. And if I put a k there, that's going to be called the kth level set of this implicit function. I'll write that here. Okay. So if you have S equals to x comma y such that, everybody can read this notation. Anybody who has difficulties in reading, please let me know. This is a set of xy points such that f of xy equals to some scalar k. So k is in R. Okay, this is known as the kth level set of f. Okay, kth level set of f, right? Now if my function f is bivariate, then the level sets would be curves, one-dimensional curves. If my function f is trivariate, then my level sets would be surfaces, right? Surfaces are two-dimensional manifolds, two-dimensional entities, okay, just like your sheet of paper, right? How many parameters do you need to represent a surface? 2. So there is some relation between the manifold and the number of parameters needed, right, in the parametric form. Okay, coming back to the implicit form, this the implicit function trivariate is going to represent 2. In this sense, there could be complicated ways in which trivariate could represent a curve as well. Can you give me an example? 2 trivariate, so you need 2 trivariate function. For example, you could have an intersection of 2 spheres, and that's going to give me 1 circle in 3D space, right? So please keep in your mind the dimensionality of the space can be different from the dimensionality of the shape or the object. I can, for example, embed a one-dimensional curve in a 3-dimensional space, or a 2-dimensional surface in a 3-dimensional space, or a one-dimensional or zero-dimensional object in a two-dimensional, whatever, right? The dimensionality of the object cannot be more than the dimensionality of the space in which it is being embedded, right? But you got the point, right? So I can have two spheres that can intersect, and similarly my expression here is gonna get complicated, right? It's going to satisfy both of these spheres, and that would exactly happen at the, are you guys able to visualize that? The two spheres and they intersect, and it's going to be one circle that you know, they meet at, and that's the curve that I'm talking about. So in this case both spheres are trivariate, right? It's going to have, what would be the implicit function of a sphere? Could somebody tell me? You can erase this, right? Yeah. Equation of a implicit equation of a sphere. Yes. X square plus y square plus z square plus r square minus r square equals 0. Yeah, no, not 0. This is an implicit form. So you would say f of x comma y comma z equals to this. That's my implicit function. And this is a sphere. Please be very specific. It's a sphere centered at the origin with radius r. So if I were to have certain center, then I would say x minus x naught squared plus y minus y naught squared plus z, whatever, blah blah blah. Okay, you got it, right? So I could have one of these such spheres and then another sphere taken into, I mean, in the set notation I have to have this and this, where, you know, fxy equals to 0, f1xy equals to 0, f2xy equals to 0. Gets a little complicated, but anyway, you can do that potentially, right? So that's my circle, and let me quickly show you some demo now. The MATLAB window here. Listen.